Hi, today we are going to talk about Ariadne, which is a static analysis and graph theory based tool that created to identify access control inconsistencies in Android ROMs that are caused by data driven customization. So let's get to it. Here you can see on the screen a example taken from a Xiaomi ROM, which shows two different APIs. The first one is called get extensions, whereas the second one is has extensions. Now, the thing to note here is typical of these APIs is that they operate on global framework variables. In this case, this variable is M extensions, and it performs some kinds of operations on these variables. These variables are global state holders that maintain some kind of state within the Android service. We call these variables data holders. Typically, the APIs perform operations on these data holder variables to either extract or modify these state information. Here in this case, we can see that the first API called get extensions is a getter, whereas the second API has extensions, checks for an existence of a key within this data holder. Now, the thing to note here is the semantics of the operations performed by these APIs on the data holder matter because they can dictate the access controls that are needed for these APIs. In this particular example, we can see that the existence check API enforces a system level access control, whereas the getter API does not enforce any access control at all. This seems counterintuitive because we can say that the existence check operation can actually be performed using the getter operation itself. So ideally, we would expect that an access control that is as strict as the has extension should also be enforced by get extensions API. But this is clearly not the case here. So this is an example of an inconsistency that can exist um, within the framework APIs that we can identify using these access control implications related to the data holders. Another kinds of hint that we can rely on are Java object semantics. For example, you have a particular class and a field within this class. You have two different getter APIs. The first one only returns the specific field, whereas the second one returns the entire object of the class. Now, due to this membership relation between the class and the field, we can say that the getter API specific to the field um, and the getter API specific to the entire class object also share an access control implication. That is, the class object getter should be at least as much protected as the field getter. So this is another kind of relation that we can use to infer access controls on APIs. Now, even though this entire task of access control implication seems relatively straightforward, it faces a lot of different challenges. We are going to look at some of them here in more details. The first one is it needs very precise data flow analysis, which needs to include field and object sensitivity. The second challenge we face is actually very straightforward. That is, the data flow analysis, due to its precise nature, is very compute extensive and expensive in nature. So the analysis scope that we define that this data flow analysis needs to be done needs to be very precise and it needs to be very selective because otherwise the entire tool cannot scale. The third challenge that we find is the sheer diverse data types that we find on the framework variables or data holders. Their structures, the types such as collections, they are completely arbitrary, and we need to account for all these structures so that we can accurately and precisely take advantage of the relationship between these diverse data holders. Let's look at an example taken from a ZTE-ROM to understand one of these challenges, specifically the precise data flow analysis. So here you can see, again, two different APIs called set alarm align type and set lock screen clean type on the right side. Now, as we can see here, if we trace the code, we find that both these API operate on the two different data holders, which both extend from the same base class called base optimizer controller. And eventually, both these APIs perform the same operation on the same variable within this parent class called mSettingsMap. So if our data flow analysis was not precise enough, it would flag this as an inconsistency because set lock screen clean type does not enforce any access control, whereas this other API set alarm align type enforces a particular permission based access control. But this is not accurate because if you look at the variables on which these APIs operate, they are two completely different objects of the same parent class. So the copy of this M setting map memory that is being modified here is completely different for both these APIs. So it is perfectly fine for both these APIs to not enforce the same kinds of access controls because in reality, on runtime, they do not share anything between the two. So this clearly demonstrates that if our data flow analysis is not precise enough, it can very quickly run into false positives. Two other major challenges that we face are the first one is inherent ambiguity. So, for example, the implications of access controls that we can derive are uncertain. And we are going to look at some of the examples of these uncertain implications. And then the last one is modeling the semantics of the operation. So, for example, we find that the semantics themselves are varying in nature, and they also operate on different granularity. So here we can look at this as an example. So if we go back to our original example in the Xiaomi ROM, if you remember, we had this parent-child relationship between a class and its field member. Um, One way of this relationship is deterministic. That is, if a field getter is protected by a certain access control, its parent class should also be protected by at least as sensitive as the field one of an access control. But the other way is non-deterministic. So if there is a getter on the parent class, you cannot say for certain that the same level of access control should exist on each of the child members, but at least one of them needs to be similarly protected. So here we see that the other way around, the second um, access control implication is actually uncertain. And we need to take into account these uncertainties when we utilize these relations to infer access controls. The last challenge is identifying the semantics and the granularity. So here again, we have yet another example from a Xiaomi ROM. And as you can see here, the API called get device owner user restrictions is a getter in essence, but it is not really a simple getter. What it does is it iterates over a particular data holder, which again is the M extensions, and then filters out certain values and only returns a subset of all the values that exist in M extensions. So here we see that this is indeed a getter, but on a different granularity. It only returns some members of a particular collection data holder that we have. So To solve these problems and to accurately identify access control inconsistencies, we propose Ariadne, which works in two broad phases. The first phase is um, a static analysis based uh, phase, which essentially analyzes the decompiled ROM and creates something that we call access control dependency graphs. So these are abstract models that we propose to model the diverse data holder structures. And the first phase is responsible to statically analyze the code base of Android ROM and create these access control dependency graphs. We'll see in more details how these graphs are actually created. So what it does is, in the first stage, it performs target variable selection to solve the first challenge of defining the scope precisely. It then um, um, extracts the type information from these variables and creates the access control dependency graph. It also analyzes the APIs and extracts the access control that are enforced on these APIs, creates access control annotations for the graph that we created, and then annotates the graph through these access control annotations. In the next phase, what we do is we utilize this access control dependency graph to infer the actual access controls that might be missing. So the first thing that we do is we quantify the uncertainty of the relations using something that we call a reduction factors. You will see again what these means. And then using these reduction factors, we propagate the access control annotations throughout the AC dependency graph to uh, arrive at final access control annotations for each of the data holders. Using these final annotations, we compare them with the access control that are present in the system, and we find the likely access control. So let's look at each of these stages in more details. So firstly, the intuition of this entire pipeline comes from a well-known concept, which is taint tracking. So taint tracking, in essence, works by tainting sources of sensitive data and then following through the entire system, the propagation of this taint, and understanding where it eventually reaches. So the key idea remains similar. We systematically trace how the dependencies flow throughout the framework, but instead of sensitive data, we use access control um, to propagate throughout this entire framework, and we find where these access controls land eventually, and through that we identify the access control that should exist. To solve the first challenge, we exclude some variables, such as local variables, variables that are inaccessible to app, and so on. We also exclude non-self-contained variables because we found through manual analysis that they don't really contribute much towards the data-driven flaws that we are trying to find. More details are there in the paper. Um, so let's understand more about what the access control dependency graphs are. So the nodes in these graphs are the framework variables, which are data holders and their members. Um, we also introduced two specific nodes to model the granularity that we were looking at. These synthetic members model whether the operation is being performed on some or all members of the collection. The edges of the access control dependency graphs are access control implications due to the operations that the APIs perform on the data holders as well as the relations between the data holders. So some examples of these edges are member to containing class relation, class to member field, specific to generic, sibling relations, and so on. Most of these relations are uncertain in nature, so we do need to quantify and take into account this uncertainty when we are utilizing these relations. So let's look at a particular example to understand how Ariadne constructs these graphs. So here on the left side, you see a Xiaomi code snippet. um, and on the right side, you see the access control dependency graph that is created by Ariadne. We'll see how this entire graph gets created. So the first thing that Ariadne does is it looks at the data holder that is being analyzed, which is M extensions, and creates a particular first node that we see here on the right, on the top. Then it looks at the structure of the type of this particular M extensions node, and we see that it is a collection, which is an array list of user restrictions. So that ends up creating the second node that you see on the right. And it also adds this contains member relation between these two nodes. Next, we see that the API get user restrictions is actually a getter API. And what it does is it operates on all members of the user restriction collection. So we create two synthetic nodes, all and some, which represent the granularity of the operation that is being performed on the user restrictions collection. Next, we see that there is one more API which only acts on some members of this entire collection. So for that, we create the synthetic member sum, as you see on the right side. Finally, we look at the structure of user restriction itself, which only contains two primitive variables. So we create one node for each of those primitive field members. And that concludes the creation of access control dependency graph for this particular case. Next, we see how the propagation happens. So now that we have the access control dependency graph, we need to utilize this graph and the access control annotations to identify the inferred access controls on each data holder. So what the way we do this is we use selective flooding so that we don't back propagate the access controls. We use something called as relevance weights. So think about this as your typical flow graph. So you start with a very high relevance weight, which is 0.95 or 0.99. And what we do is we propagate the access control annotations through the relations, and each relation is assigned a particular reduction factor which quantifies the uncertainty of that particular relation. So think about two access control dependency graph nodes which are siblings of each other. So in this case, what would happen is the uncertainty that one access control should also be applied to another sibling node is, let's say, 70%. So in this case, the relevance weight of the propagated access control will decrease to 70% of its original weight. This quantifies that the relation itself is uncertain, so that we know that the confidence of the access control um, uh, annotation that has reached to the sink is now less than what it was to begin with. So this allows us to define reduction factors for each of the relation based on the uncertainty associated with this. More details about these reduction factors and how we came up with them are in the paper. But the crux of it is the raw values don't really matter that much. We also performed experiments on it, and what we found was the relative difference between these values are the thing that matters, especially when you have multiple hints for each of the inference. Finally, to identify the inconsistency, what we do is each of the data holder is contains a ranked list of final access control annotations with the ranking relevant to their eventual relevance weight. So what we do is we propagate these access controls directly to the APIs that operate on these data holders, and then we compare these access controls with the actual access control that exists. If there is, if the inferred access control is stricter than the actual access control that exists, we flag this as an inconsistency. Um, we evaluate Ariadne on 13 different farms, and which spans 8 vendors, including Samsung, Xiaomi, ZTE, and so on, and spanning versions, Android versions 8 through Android version 14. And we found that Ariadne achieves around 97% API when applied on AOSP ROMs, because AOSP ROMs are the ones where we have ground truth. We assume that all AOSP APIs are perfectly secure, which is in line with the previous work. So this allows us to identify false positives, and the accuracy that we get is about 97%. We also identify 90 unique inconsistencies, out of which we build 13 proof of concept exploits, for most of which we actually received an acknowledgement. And the thing that we want to emphasize here is we don't advertise Ariadne as a one-stop solution to all your access control problems. It exists to cover a specific gap that was left by a lot of different previous books. So the best way to utilize Ariadne is to use it alongside other prior tools such as Poirot or AC Miner, um, which would give you a more comprehensive coverage of the access control inconsistencies that can be found. We also perform comparison with these existing tools in our paper. So when we do this comparison, we found that the Ariadne identifies 30 new inconsistencies compared to prior ones. So this concludes my presentation to Ariadne. More details are there in the paper. The source code of Ariadne is open source. You can also find us at the SST research group. Thank you so much for listening.